all the men and women of the world. Happy Women's Day, which was yesterday. Today I will tell one quote about women which had told Swami Vivekananda. In my earlier video, I had told about uniform convergence of a sequence of function and M.N. test about the uniform convergence of sequence of function. Today, I will say uniform convergence of sequence of differentiable function. First question is, if each Fn is differentiable at the point, consider the point is arbitrary point C, that implies must f is differentiable at the point C. Consider this function fnx equal to x to the power 1 plus 1 over 2n minus 1, which is defined on the closed interval minus 1 to 1. Obviously, this sequence of function converges to mod x. Just see the pointwise limit. This is easy type, and the graph is look like such type. Notice when n equal to 1, then this value is similar to x square. So graph is look like such type. N equal to 1, here n equal to 1, n equal to 2, and when the function tends to infinity, then the limit would be mod x. Okay? And notice here one interesting thing. Fn dash x equal to 2n over 2n minus 1 times x to the power 1 over 2n minus 1. Here f prime 0 equal to 0. That means the derivative function is differentiable at the point 0. But here look, the function f not differentiable at the point 0. Okay? That means if fn is differentiable at the point C, that does not imply f is differentiable at the point C. Okay? Now I will see one interesting theorem about differentiability. Differentiable limit theorem is, suppose fn converges to f pointwise on the closed interval ab, and assume that each fn is differentiable. If fn dash converges uniformly on the interval closed ab to a function g, then fn converges to f uniformly and f is differentiable, and f dash equal to nothing but only z. The original idea is fn prime converges to g uniformly, then this g is actually same to f prime. Okay? This theorem is more important to find the uniform continuity of a sequence of function more easy. Just at first see one question. Fnx equal to nx plus x square over 2n, which is defined on minus c to c. Here the closed interval. At first see the limit, pointwise limit. If you check, this function actually converges to the function fx equal to x over 2. That means here fn converges to x over 2 which is a. Now my question, is this convergence is uniform convergence? Let's see. Now to find the uniform convergence, I will use above theorem. Notice Fn dash equal to obviously half plus x over n, and obviously this Fn dash pointwise converges to half. That means actually gx equal to half. Now we have to check, is this convergence is uniform convergence? That means, is Fn dash converges to gx uniformly? That means we have to check Fn dash x minus half, which is equal to, just put the value, this value would be absolute value of x over n. We have to prove this is actually less than epsilon. But since Fn is defined on the interval close minus c to c, then obviously this guy less than equal to c over n. Then let epsilon greater than 0, there exists capital N who is greater than c over epsilon, and for all n greater than equal to capital N, obviously this value would be c over capital N. That means if you put the value, then this value would be actually less than epsilon. Means Fn dash converges to the function gx equal to half uniformly. Okay? Since Fn dash converges to gx equal to half uniformly, that means our given function Fn converges to f which is equal to x over 2 is obviously uniformly, and this g is nothing but this is actually f dash x. Okay, because fx equal to x over 2. Now see, recall our before function. In this function, fnx converges pointwise in the mod x function, but this convergence not uniform converges, because here fn dash equal to this, and if you put the limit, then limit if x equal to 0, then limit n tends to infinity fn dash x equal to actually 0, and when x greater than 0, then limit n tends to infinity fn dash x equal to 1, and if x less than 0, then limit n tends to infinity fn dash equal to minus 1. That means limit n tends to infinity fn dash equal to, which is actually equal to gx function, this is when x equal to 0, then this value is equal to 0, when x greater than 0, this value equal to 1, and when x less than 0, this value equal to minus 1. And since gx not be continuous function, so obviously fn dash does not converge to gx uniformly. So our main sequence of function does not converges to mod x uniformly. Are you getting? Well, converse of the theorem it does not necessary condition. If fn prime converges to g uniformly, then we can tell obviously fn converges to f uniformly, and where obviously f prime equal to g, but uniform convergence of fn and even differentiability of the function f tells us nothing about the fn prime. Are you getting the idea? Now I will see one example which had come in N.B.H.M exam 2020. Question is, for a positive integer n, f(n)x which is defined from R to R be defined as f(n)x equal to x over 1 plus nx square. Then for each of the following statement, state whether it is true or false. Option 1. The sequence f(n)x of the function converges uniformly on R. Option 2. The sequence of the function f(n)x of the function converges uniformly on the set closed to 1b for b greater than 1. Option 3 indicate the sequence fn'(x) which is derivative of the function converges uniformly on R. And option 4 indicate the sequence fn'(x) which is also derivative of the function converges uniformly on the closed interval similar to before, where for any b greater than 1. Okay, let's verify the option fn which is defined from R to R such that fn(x) equal to x over 1 plus nx square. Limit n tends to infinity. Obviously this limit is 0. This is defined for all x belongs to R. That implies obviously fn converges to pointwise. Now I will see is this function is uniform convergent. Notice the function x over 1 plus nx square. When the value will be increased, this value would be less than equal to 1. That means obviously this function is bounded in whole real number. So here we can apply the M.N test to find the uniformly convergence. M.N test is supremum x belongs to R, absolute value of fn(x) minus fx. Since fx equal to 0, that means this value would be supremum x belongs to R, x over 1 plus nx square. And obviously fn defined from R to R, that means we have to find the supremum value. Here x belongs to whole real number. Let us know to find the maximum of fn(x), at first we have to find f'(nx) equal to 0. Suppose x0 is a solution of this equation, then if f'(n) x0 less than 0, then the sequence of function fn(x) has a maximum at the point x0. To find the maximum, at first we have to find f'(nx) equal to 0. And if we find the f'(nx), then this value would be 1 minus nx square over 1 plus nx square whole square. If we put the value at this equation, then you will get at the point x equal to plus minus 1 over square root of n, the function fn dash x would be vanishes. Okay, that means at the point 1 over square root of n, the function has a maximum value. Now put the value, this value would be 1 over square root of n over 1 plus n into 1 over square root of n whole square. This value would be 1 over 2 square root of n. And as limit n tends to infinity, 1 over 2 square root of n equal to 0. That means I have got this supremum value tends to 0 as n tends to infinity. Therefore, obviously this function is uniformly convergent in whole real line. Okay? Option 1 is a right option. the sequence Fn of the function converges uniformly on whole real line. So, the second option also right option, because second option indicate sequence of function Fnx converges uniformly on the closed interval 1b where for all b greater than 1. So second option is right option because this function is uniformly convergent on whole real number. The third option indicates sequence of function Fn prime x, which is derivative of the function, converges uniformly on R. See the Fn dash x, which is equal to, just find the derivative of this function. This is would be 1 minus nx square over 1 plus nx square to the power whole square. If we find the limit, then this value would be 1 when x equal to 0, and when x not equal to 0, then the value would be 0. That implies Fn dash x is a discontinuous function on whole real line. That means Fn dash x is not convergent uniformly on the real number R. Option 3 is a wrong option. The sequence of function Fn dash, which is derivative of Fn, converges uniformly on R. This is wrong option. Similarly, option 4 also wrong option because this is indicate the sequence of function Fn prime x, which is derivative of the function, converges uniformly on the set close interval 1b, and this is true for any b greater than 1. This is also wrong option. Are you getting? Here I have seen one sequence of function which converges uniformly on R, but their derivative does not converges uniformly. That means converse of the theorem does not true. If Fn dash converges to uniformly, that always imply Fn is uniform convergent. But if Fn uniformly convergent, that does not always imply Fn dash be uniformly convergent function. Are you getting? Oh, yeah, I will stop here. I will highly recommend you please see the today's video with pay attention, because this video is very important for any competitive exam, and do subscribe my channel for more videos and do share to your friends of my channel. Stay safe and stay positive always. Thank you so much.